Hi everyone, I'm Amogh, second year grad student in Dr. Washerman's group. And today I'll be talking about Skyrmion Racetrack Memories. Sorry. Um, so, I'm sorry. So I'll go over the introduction and properties of the Skyrmions. I think Jack covered a few of them briefly, so I'll try to make it quick. And then I'll talk about the DMI, the Skyrmion Hall effect, and then cover the racetrack memories, where the presence of Skyrmion is 1, absence is 0. We'll see how to create and annihilate Skyrmions and briefly see applications in bottleneck. So let's get started. Skyrmions are quasi-particles with chiral spin configurations. Chirality is the property where the object and its mirror image can't be superimposed, like the example on the right. It's found in non-centrosymmetric lattices, which means they have no center of symmetry, like the figure on the right, where the ion in the center is off the center. Usually, we make skyrmions with ultra-thin films deposited over heavy metals, but we also have bulk skyrmions, and it was first found in manganese monosilicide in 2009. Skyrmions are basically solitons, which is a class of particles which are like they have a fixed shape in a given material and are highly stable. So there are two types, block and anneal. So as you see in the figure on the right, the anneal skyrmions have the spin oriented radially, whereas in the block skyrmions they're perpendicular to the radial axis. So they're associated with the topological quantum number, and since it's a quantized value of plus or minus 1, they have a topological stability, which means it's there's an energy barrier required to break them. So in the exchange interactions that we studied in class, we had them either parallel or anti-parallel to each other, but here you can see that that's not the case. And why they're stable even then is because something called as Dzhalosinski-Moria interactions, or DMI for short. It's in systems with lack inversion symmetry, and the spin orbit coupling. It's found in materials with high spin orbit coupling, and this this enables an asymmetric exchange interaction, meaning the spins can be inclined at an angle to each other instead of being parallel or anti-parallel. And the micromagnetic energy is given by the equation below, where D is called the DM factor. So higher the D, higher the DMI interaction, DMI. So the figure on the right, top figure on the right is one of an ultra-thin film on a heavy metal. And the other figure below it is of the different phases you see as you increase the D. So for a low D, we have a saturated ferromagnetic state. And when you increase the D, it's isolated skyrmions, and then a skyrmion lattice, and then spin spirals. Coming to skyrmion Hall effect, if you guys will already know what a Hall effect is. If you have a electric field across a strip and you have magnetic field perpendicular to the plane of the strip, you will basically have a transverse electric field in the strip. If skyrmion Hall effect is basically the same, except you have motion of the skyrmions instead of the electrons. So we have a transverse velocity as well as a longitudinal velocity. And one more point is that skyrmions usually repel the edge of the racetrack. It's because of their topological protection that they don't want to approach the discontinuity in the strip. So if you have a reasonable current applied, the transverse velocity and the repulsion from the edge will cancel out, and you'll eventually have a plane longitudinal motion. Coming to the figure on top, let's say you introduce a notch in the racetrack, what happens then? So the figure on the right shows the energy profile as the skyrmion approaches the notch. So you see a very high energy barrier which is created, and that varies for different Ds. And it's been simulated and also seen that higher the D, larger the skyrmion is. So larger the skyrmion, you have the one in the red has the highest energy to cross over the notch. This could be a potential application in long-term memory storage because this will simulated to have a stability of more than a few years. And there is also loss associated with skyrmions in this configuration. Suppose if you have a large current passing through, you will not give this skyrmion time to like stabilize and have a longitudinal motion. It will basically just reach the edge and like annihilate. Coming to racetrack memories, it's basically a nano magnetic strip with presence of skyrmion being 1 and absence being 0. It was initially proposed for a domain wall racetrack. But you can, as you see in the table here, skyrmions like outperform them in almost all the sections except the reed margin. This is particularly because the skyrmions are very small in size, of a few nanometers in radius. So this makes it very hard to read them compared to the domain walls. And one of the architectures proposed was to have a conversion between domain wall and skyrmions. So whenever you want it to be read, you can convert it to a domain wall at the readout head. Okay, coming to how do you create an annihilate and shift them? First one is from experimental result from a paper in 2015, where you have strip domains passing through a congested structure, leading to the generation of skyrmions. Next is the one in 2021, which apparently they claim that this is the first paper where they showed the creation, movement, and annihilation all in the same material system on the same setup that is. So how it works is you have a current going in like perpendicular to the plane of the material. And when you have a pulse acting through the channel, so as I was saying, when you apply the pulse, it will create a disturbance in the spin orientation, and when you have magnetic field, it stabilizes, leading to a nucleation of a skyrmion. Then you can use a field in plane, a pulse in plane with the material to cause the movement of the skyrmions. In a similar way, if you apply a negative pulse to the source and move the skyrmions near the source, this leads to the annihilation of the skyrmions. And the figure on the right is different ways of reading the skyrmions. First is using a magnetic tunnel junction. So this leads to a variation in the magnetic current observed in the presence and absence of skyrmions. And finally, here's something called a topological Hall effect, which basically means when you have a skyrmion moving through a racetrack, you'll also notice a transverse voltage, and you can access this through contacts. And these are some of the applications. This is one from 2015 where they basically use a conversion between domain walls and skyrmions to implement logic. And the figure on the right is one we will see in Dr. Friedman's talk from UT Dallas. He talks about the dynamics of skyrmion logic. This was a paper from 2022. And there was also a paper regarding using skyrmions in cache devices. So I guess most of the papers I've seen till now have been simulations and not actual results. So some of the bottlenecks are these points below. First is the effect of thermal fluctuation on the skyrmion motion, which is not avoidable. And then is the roughness, edge roughness, which will definitely like slow or lead to ejection. This is very visible on the graph here, where ideally we have a given velocity, but due to the temperature and roughness effects, the velocity changes. This will lead to a change in the distance between skyrmions, which will basically like invalidate the stream of its use. There's also skyrmion pinning, which happens due to the interface between skyrmion and magnetic material and the heavy metal. And till now, we spoke about skyrmions with DM interactions, but there are few others which will affect the stability, and the dynamics of them have not been studied yet. And we also assume that there's huge barrier between the ferromagnetic and skyrmion phase, but fluctuations in the magnetic field will can cause the phase to revert to ferromagnetic states, hence deleting all the skyrmions. I would like to conclude by saying that there are many limitations to overcome, but the field still is in infancy. So at least experimentally, we have a long way to go. But once we succeed, we'll have a highly dense, robust, and fast memory. These are some of my references, and thank you for listening.